Hey guys, so in this video we're going to be discussing the integrated rate laws, and we're going to be talking about how these integrated rate laws are actually providing us a relationship between the concentration of our reactant and the time of the reaction. So here's a summary of the different rate law information we know. We know the traditional rate law where rate is going to be equal to K times the concentration of our reactant raised to the N, where N is the order of the reaction. So usually we see orders that are integers of 0, 1, or 2, although in our previous video we did see an example where the order was a fraction. We know that the different orders, so this exponent of the concentration, ultimately leads to a change in the units of our rate constant K. And remember, our general trend here is that as we go from 0 to first and first to second, we're dividing by a unit of molarity. And we've also discussed how our integrated rate laws can be derived from our traditional rate laws, and all of our integrated rate laws are analogous to y equals mx plus b. And so this relationship allows us to be able to actually plot the corresponding x versus y for a certain order reaction and yield a linear line, where the slope is going to be equal to the analogous m of the respective equation, and the y-intercept is going to be equal to the b value in the respective equation of the line. So now let's actually practice plugging values into these integrated rate laws. So for example, in this problem, we're given the tabulated data that shows the concentration of N2O5 versus the time of the reaction. We're supposed to determine the order of the reaction and the value of the rate constant K. And so because we're given these two pieces of data, we can figure out the order of the reaction, remember, from graphing 0, first, and second order plots. I was able to determine this was a first order reaction because when graphing time versus the natural logarithm of the reactant concentration, we had a linear relationship. And here's the equation for the line that was obtained. And so we know the order of the reaction now is the first order reaction, and the value of the rate constant, remember, is going to be equal to the opposite of the slope. So our K is equal to 0.0078 1 over seconds. Now the next question we're asked is to predict the concentration of N2O5 at 250 seconds. So we need to know the concentration at a certain time, and the certain time is 250 seconds. And so remember that we use the integrated rate laws to relate concentration and time. So the integrated rate law for a first order reaction is the natural logarithm of the concentration of the reactant at a certain time is equal to the negative rate constant times that time plus the natural logarithm of the initial reactant concentration. Now this reactant concentration at a certain time is what we're solving for. We know the rate constant from our plot is 0.0078 inverse seconds, and our time is 250 seconds. So make sure that when you're plugging these values in, that the time is actually in the correct units corresponding to your rate constant so that those units will cancel. Then we're going to add the natural logarithm of the initial concentration, and referring back to our chart, we can see that the initial concentration is 1.000 molarity. So that's the concentration at time 0 of the reaction. So we can say the natural logarithm of 1.000, and so we can actually slightly simplify this equation because the natural logarithm of 1 is actually equal to 0. So in this case, we have the natural logarithm of the concentration at a certain time is equal to our negative rate constant times time, which is actually the value of negative 1.95. And this is a unitless factor because 1 over seconds cancels with seconds. Now in order to just get our concentration at a certain time, we need to take the e of both sides because e is the opposite of the natural logarithm, so those will cancel, and ultimately our concentration at a time is equal to e to the 1.95, which is 0.142 molar. So what this tells us is that at 250 seconds, after the reaction has proceeded for 250 seconds, our concentration has decreased from 1.000 to a concentration of 0.142 molarity. Now our next example says that the decomposition of SO2Cl2 is first order with respect to SO2Cl2 and has a rate constant of 1.42 times 10 to the negative fourth inverse seconds at a certain temperature. How long will it take for the reaction of SO2Cl2 to decrease to 25% of its initial concentration? So again, we know this is a first order reaction, so we're going to be using that integrated rate law for first order. We're given our rate constant K, and we're trying to solve for the time that it takes for the reactant to decrease to 25% of its initial concentration. So our initial concentration actually isn't provided to us. However, because we're given this in terms of percent, we know that it'll decrease to 25% of the initial concentration. We can assume that our initial concentration is going to be 1. And so this means that our concentration after it's decreased to 25% is going to be 0.25. So we know that the natural logarithm of 1 is going to be 0, so that slightly simplifies our equation. And if we divide by the negative rate constant on both sides, we'll be able to solve for t, which is our time. And so the value of time in this problem ends up being 9,762 seconds. So that is how long it takes for our reactant to decrease to 25% of the initial reactant concentration. Now the next question is, if the initial concentration of the SO2Cl2 is 0.150 molar, what is the concentration of the SO2Cl2 after 2.0010 to the second seconds? And so again, we'll still be using this first order rate law. Our rate constant, which was given to us previously, is 1.42 times 10 to the negative fourth inverse seconds. So we're trying to solve for this concentration at the time that's given to us. So we can plug in our rate constant, plug in the given time, plus the natural logarithm of the initial concentration, which was given to us in the problem as 0.150 molar. So we can solve for this quantity using our calculator, and we end up getting that the natural logarithm of the concentration at this given time is negative 1.90. But remember, we're not done solving for just the concentration of the reactant at this time. We need to take the E of both sides, so this cancels, and our concentration at a time is going to be equal to e to the negative 1.90, which is ultimately going to be equal to 0.150. And the units are going to be molarity because this is concentration. So in this video, we've seen how we can use integrated rate laws to solve for different variables, such as time and reactant concentration at a time. You can also use integrated rate laws to solve for the rate constant K, and even solve for the initial concentration of the reactant.